contributions to different aspects of coupled ocean atmosphere climate dynamics. And that's really that variety and that broad perspective are what part of what makes him a great Nobel lecturer this year. He's thought about El Nino southern oscillation and tropical ocean atmosphere coupling, overturning circulations in the ocean and present, past, and future climates. He's thought about glacial cycles, including snowball Earth, path-warm climates, and abrupt climate changes as the climate system jumps between those different states. And his work is also extended into atmospheric science, in all the context of climate variability, understanding the atmospheric circulation, and the role of clouds in maintaining warm climates, and even in the stratosphere, which is a topic that we've spent a lot of time thinking about here in Toronto. Going back to his kind of beginnings, I guess, I think I remember meeting Professor Tziperman first at the Geophysical Fluid Dynamics Laboratory, where he was a visiting professor at that point. I think it was in the 1990s, a long time ago. And he was really keen to work hands-on with the modular ocean model, which was in its early versions at that time. That's what I remember. And I remember being really engaged in that. And the lab was kind of a buzz about his work on that. He was working in ocean data assimilation at the time, and just a really hands-on technical person with deep insight into ocean dynamics. We also had some great discussions about GFDL and the early days of GFDL, the AM series of models at that time. That's what I remember. And this hands-on approach, the spirit of technical exploration, and the insight into what climate models can tell us, I think is really going to become apparent during this week's lectures. And it's really fundamental, that technical understanding to advances in these different areas of climate science. So in 2003, he moved from his first academic position at Weizmann to Harvard. He's the recipient of the Professor E.D. Berkman Memorial Award and holds the Pamela and Vasco McCoy Jr. Professorship of Oceanography and Applied Physics. He's an engaged educator whose website is full of useful resources in physical oceanography and climate, including many models, lots of codes, working codes, exercises, and really nice photos. And some of this material has been published separately as a new book, Global Warming Science, a Quantitative Introduction to Climate Change and Its Consequences, which is very nice, and I assume will be at least part of your lectures in some way, some of that material. As a supervisor, he's graduated many very influential scientists in our field. For example, Yochai Caspi, Peter Kuipers, Ian Eisenman, Laura Zana. These are all people we've met and come through our department, our program. And I think this kind of educational engagement, above all, makes him a perfect Nobel lecturer because we put our lecturers to work. They spend all day, they spend a lot of time before getting here preparing their lectures, and then they spend a lot of time in meetings that extend throughout the day. And I understand that you've also extended your availability so that you could have additional one-on-one appointments. So there are still some open slots now that I encourage those of you in the group to sign up for. So this set of lectures this week reflect his commitment to research, scholarship, and education in the broadest sense. They range across scientifically and societally relevant topics like the role of clouds in keeping the planet system warm, how fluid turbulence shapes the ocean circulation, how the processes at the highest level of the atmosphere control cold weather extremes here on the ground, and how planetary bodies from Earth to Europa end up being ice covered. But today is going to focus on one of the big problems in climate science, or maybe two, okay? Applied climate science in the area of hydroclimate of California, and this new trend towards attribution of climate events and how it's not so simple. So I want to thank Professor Tziperman in advance for spending the week with us, and I ask you to join me in welcoming him.
Thank you. And hopefully everyone can hear me without the microphone. It's not that big a room. Let's see, do we have a pointer here? Or do I use my mouse on the... Okay, never mind, I'll make it work. Okay, so amazing, thank you. Great, thanks. All right. Amazing. Okay. Yeah, thanks for the introduction. I'm looking forward to this, and I'm happy to meet anyone, obviously. So I'm trying to be very ambitious, and I'm trying to stick 2 talks into this one slot. So let's see if I can make it. So starting from the first one, this is the work of Min Fu, who was a student with me, and now he's a postdoc in Yale. And the idea there is that many regions of the world that are semi-arid right now, mid-latitude regions, are projected to be drier in a future warm climate. It turns out that the last time the CO2 was higher naturally, that was about 2 to 5 million years ago, a period called the Pliocene. And it turns out at that time, California, for example, but these other sites as well, was actually very, very wet. So the desert, the deserts in California were actually the location of lakes, as I'll show you. So the question is, what can we learn from that? And why is it that climate models don't produce this? And we'll try to propose a feedback that is missing from climate models and might explain why is it that we should actually expect California and the west and the southwest US, for example, and I'll show you that there are other areas, to actually be wetter rather than drier. So please interrupt me with questions at any point. Let's start with the California droughts in the news. So the New York Times shows you this lake bed that is very dry. This used to be a lake. Another dry area. This is the ex-governor of California signing documents that restrict lawn watering and so on and so forth. So, and here's the scientific part of this. So this is a paper from a few years ago that says that this drought event in California was the most severe in the last 100 years. So it's not just in the New York Times, it's also in the papers. The claim is that the current droughts in the last decade or so are as strong as they've been in the last 1,000 years. That's a pretty dramatic claim. And obviously the implication is that in a warmer future, California would get even drier. Okay, however, if you have listened to the radio recently, you've heard about atmospheric rivers and so on, and you wonder whether we should worry about California floods. So same source, the New York Times shows this picture, and there's this wonderful text here which says the coming California megastorm, and California is facing the threat of another kind of calamity. We're talking atmospheric rivers that will bring a huge amount of moisture all the way from Hawaii to California, and the amount of moisture is 26 times the Mississippi River, and that would be the consequence. And here's a picture of an atmospheric river. So what this is water vapor in the atmosphere that does transport a huge amount of moisture, and the claim now in this article is exactly the opposite of the ones we saw in the previous slide. And here the claim is that California would get drier, much, much wetter. So you wonder, okay, which one is correct? Any questions so far? I'm hoping you're all confused by this point. Okay, great. Okay, so what do the scientific projections tell us about the future California? So you look at this and you see green means wetter and yellow means drier, and California is sort of the boundary in the southwest US. It might get wetter, might get drier. You can't learn a lot from that. You look at 2 different specific climate models. This is soil moisture in the southwest US. One model shows no change basically all the way to 2100, and the other one shows a very, very dramatic drought. So again, the models are not very consistent, and we can't rely on them for a projection of whether this area of the US will get drier or wetter. Okay. Yeah, let me stop here for a second and see if there are any questions. Please. If you're going to be around at that time, you'll find out. Let's see. I'm planning to be around until this point. Yeah, I mean, for now, they're both correct. In the future, who knows? Yeah.
Well, one is, I think the question is, Miroc looks biased. Looks biased.
Possibly, but it's interesting. The one that's biased wet is the one who's also getting drier. So obviously, so there's some complicated behavior there. Great. Okay, so the bottom line is that we don't know what's happening. So let's try to use the past as a guideline. And the past is, again, this Pliocene. So let's talk about the Pliocene. So these are CO2 reconstructions in the Pliocene. This is the present. This is 4 million years ago. The range of CO2 estimates, as you can see, is very large. So it's all the way from 280 to 400. Normally, when you ask someone, one of these people at the community who's reconstructing CO2, they'll tell you the Pliocene had 400 ppm of CO2, which is exactly what we have now, right? We have 420 right now. Except that at that time, the climate was equilibrated with 400, and right now we've just arrived to that, so it will take some time to equilibrate. So it's a very relevant period for understanding the near future, and people think about it as the nearest past analog of a future climate change. But this tells you how big the uncertainty is in CO2. Okay, so here's the Southwest US, and every one of these blue areas is a lake. So you can see the Death Valley was a lake, and this was a lake, and that was a lake. So, I mean, it's actually surprising how wet it was in the Southwest US in that period. And there's very strong geological evidence. And we know this by looking at, you find things like that are lake sediments. You find these plankton that are typically freshwater. You find these small shrimp that are typically freshwater things. So there's plenty of evidence showing that much of California was very, very wet. And the question is, what was the mechanism that made it wet, and why isn't that climate models don't get it right? Again, feel free to interrupt. Okay, great. So that was evidence number one, was that this area was wet. Evidence number two was that there are several areas in the world, including close to California, where the temperature at that time was much, much higher. So globally, the temperature was only 3 degrees warmer than today during this Pliocene 2 to 5 million years ago. But in these upwelling areas, okay, you can see that close to California, the ocean was like 9 degrees warmer in this area, which is also an upwelling site. I'll talk about upwelling in a second. Also, the temperature was like 9, 10 degrees warmer. So is there a connection between the fact that the ocean locally was very warm and the fact that the land there was very wet? That's the claim we're going to make, and I'll try to explain what the mechanism is. This is the area of California today. So this is the temperature, and you see very cold water due to upwelling of water coming from below. Assume everyone is ocean atmospheric science here. Okay, great. Not necessarily. Okay, great. So, okay, so there's an area here where cold water is coming from the below, and this is why the coastal area is so cold, and you can see the warm area offshore. So all of this cold area was 10 degrees warmer, which is a huge warming. Okay, and this is a reminder of what is upwelling. So if this is California here, and the wind is blowing south along the coast, then due to the Coriolis force, the transport of water at the surface is to the right of that, and this water must be replaced with water from below. So this along-shore wind stress is leading to the upwelling of cold water from below. That it will be the base of much of what I will talk about today. And these are the upwelling sites in general. So I will focus on the Southwest US, but in general, you can see the similar upwelling here in Peru, the Canary Island, Benguela, and California. These are the 4 major upwelling regions that we've actually studied in this, even though I will focus mostly on the Southwest US. So this isn't a local problem, it's a problem that repeats in several areas of the globe. Okay, so we're proposing this feedback, and I'll try to explain what the feedback is and why we don't expect it to be well simulated in climate models, in current climate models. By the way, so should I be finishing at 4 o'clock? What's the? Okay. Great. Okay, great, we can do that. Okay, so the feedback has a few elements. So the idea is this: suppose the land is wetter, right? It's going to be a positive feedback. So suppose we started with the land is wetter. This turns out that this weakens this wind that drives the upwelling. Okay, wetter land weakens the wind that drives the upwelling. I'll explain why. This leads to less upwelling. The less upwelling leads to a warmer SST. That's obvious, because if you have less upwelling of cold water from below, the surface will warm. And then the warmer SST will lead to a wetter land. So that's the feedback I'm going to explain now. Okay, this is sort of an overview. Makes sense? Wetter land, weaker winds, weaker upwelling, and warmer SST, all in a one positive feedback loop. Okay, so for that, we're going to use a couple of different experiments. First, we'll specify wet land. So you can see the bluish areas here is where we specify the land to be wetter. And then we'll see what is the consequence of the land being wetter. And then we'll specify a warmer SST. This is the sea surface temperature anomaly here. We specify a warm ocean here in the upwelling zone, similar to what we see for this Pliocene period. And this will show that this leads to a wetter land. So this way we close the feedback. Wetter land leads to weaker wind, and weaker and warmer ocean leads to a wetter land. That's the plan. And these are the sets of atmospheric model experiments that we'll use for that. Morgan? You do need well-resolved topography in this area because the winds do depend on the topography. So, but it, well-resolved in the atmosphere is not as bad as well-resolved in the ocean. In the ocean, you need a resolution of 2 kilometers to resolve these upwelling sites, which we don't have. I'll talk about that later. But in the atmosphere, we need a resolution that's doable, and we've used something that's reasonable. Okay, so starting with this feedback loop, we're talking first about how wetter land leads to weaker alongshore winds. So here's the normal steady state. So you have this red thing is the Bowen ratio. Never mind if you're not familiar with that. Basically, red means that it's a desert. And what you see here is the sea level pressure is the color, and the winds are, you see the winds going around like that. I think the next one actually shows this nicer. So you have a high pressure over the Pacific, and this high pressure has the wind circulating around it because of the Coriolis force. And this part of the circulation around the Pacific high is what drives the California upwelling. Okay, great. So what happens now when you prescribe a wet land? Let's first see what happens, and then we'll see why. So you prescribe wetland, you can see that the red colors here disappeared. So this area is now wetter. And as a result of that, the wind anomaly, right, the change to the wind is in the opposite direction than the mean wind, which means that this alongshore wind is weakening. So just like I was suggesting, a wetter land leads to a weakening of this wind that drives the upwelling. Make sense? Okay, great. So in that's what we're trying to explain. And why is that the case? So for that, you need to understand why there is this Pacific high. So if you didn't have continents, you would have, there's the Hadley cell that has subsidence around 30 south and north. This would have led to a high pressure ridge like this over the entire globe. So this is a world without continents. But once you add the continents, this breaks this high pressure ridge into high pressure regions, and that's where you get this wind. So what happens when we make the land wetter is the ocean is effectively extended, and the high pressure is extended over land, and therefore the wind that circulates around the high pressure doesn't happen along the coast, it happens over the ocean, and that's why the wind weakens along the coast. So if I had to say it again in a brief sentence, the wetting of the land moves effectively the boundary between the ocean and the land toward the land itself, and therefore the winds that go around the high move over land, and that's why the wind along the coast over the ocean is actually weakening. Make sense? Okay, great. Any questions about that part of the story? Yes.
Is it a bit of weakening of the pressure gradient, like the high pressure is in?
Yes, the east-west. That's right. Exactly. This east-west pressure gradient in that area. Okay, this doesn't complete. Okay, this pressure gradient here weakens just over the ocean close to the land, and that, because of geostrophy, thermal wind, whichever, leads to a weakening of the wind. Great. Okay, so that's the first part. I think that's good enough for us. Then another. So of course, weaker wind leads to weaker upwelling. We don't need to dwell on that because the upwelling is driven by the wind, so it's kind of obvious. And then if we weaken the upwelling, you have a warmer SST because the upwelling is what brings cold water from below. If you weaken that, you don't bring cold water, you warm the surface. These are some model experiments that show that, but we don't have to worry about it. So far we've shown that wetter land leads to weaker winds, and therefore this leads all the way to weaker upwelling and warmer SST. The other part that's less trivial is what does the warm SST do to the wetness of the land? So the claim was that the warmer SST would also lead to a wet land. So we've done these experiments in which we prescribe different extents of warming. You see weak warming and large warming. And when we do that, we can run an atmospheric model and ask, okay, what does this do to the precipitation over land and why? So this is the second set of experiments. Again, we run an atmospheric model, we warm the prescribed SST, we ask what does this do to the wetness over this area that we're interested in. Okay? So these are the results. Red here means increased precipitation. So we warm the SST and we get increased precipitation in this area over land. So that's what we thought might happen. So now we have wetter land leads to weaker winds. The weaker winds leads to weaker upwelling. This leads to warmer SST. And finally, this also tells us that the warmer SST leads to a wetter land. Why? Let's explain this last part right here. Why is this connection? Why is the warmer SST leads to wetter land? So it turns out there's a couple of different mechanisms. So first of all, there's summer precipitation is increasing. And I'll talk about why in 1 second. And then in winter, you get more cyclones. So summer precipitation happens, let's just display everything here. So summer precipitation is increasing because there's more CAPE. You increase the moisture at the surface, this leads to more CAPE if you're into that sort of thing, and more CAPE leads to more precipitation in summer. During the winter, when you warm the SST, this redirects cyclones. Cyclones is what bring precipitation during winter. And when you redirect them over land, you get more precipitation over that. So the mechanism is different between winter and summer, but whichever it is, the warmer SST did lead to a wetter land as suggested. Okay, questions?
So does it make sense quantitatively? I mean, you showed the changes in wind speeds. I didn't see the scale of that. Are they comparable to is it a big perturbation that you get for a realistic change in soil moisture?
It's not negligible. Is it enough? That's a different question. I can't guarantee that. That's a good question, obviously. Yeah.
Is the redirection of cyclone tracks, is that just because it's
the sea surface temperature anomaly creates a local high-low, and then that creates a circulation that the cyclones are redirected by the circulation.
If everything else was the same, I know it couldn't, but if everything else was the same and it was a western boundary instead, would it not redirect cyclones?
I think it would. Yeah, I think it would. It's just that it's a large-scale SST perturbation, hundreds of kilometers, and this leads to an atmospheric pressure structure that leads to cyclonic, anticyclonic circulation, whichever it is, and that leads to a redirection. It's like when you have a high pressure over an area, cyclones go around that because they're redirected. So it's that sort of thing. Yeah.
So in these experiments, you're applying this perturbation to a basic state that corresponds to current conditions. But if you look back 4 million years ago, the ocean circulation.
The ocean circulation might have been different. That's right.
Thermocline to be different.
That's right.
Would you expect to see the same sort of response for the similar perturbation?
Yeah. So several things change if you go back. First of all, the vegetation over land changes, and these integrations actually take that into account. We prescribe the sea surface temperatures, so we don't have to worry about subsurface thermocline, anything there. We just prescribe the sea surface temperature. So you could ask, okay, how does this warming happen? Does it involve the thermocline moving and so on? We don't need to worry about it because we just prescribe the sea surface temperature.
But you do need to think about that if you try to use what we know from the past.
That's right. Yeah, I was going to talk about this later, but let me just comment that if you wanted to resolve all of this feedback, you'd have to resolve the ocean upwelling in the ocean model. And because that requires a resolution of 2 kilometers, it can't be done by a climate model. And that's why we have to prescribe to do these 2 sets of experiments. What is the effect of wetness on the winds, and what is the effect of the sea surface temperature on the wetness? That's why we had to break it into 2. You can't really simulate this entire feedback. Okay, concluding this part. So, there's the claim in many attributions that the Southwest is getting drier. The past shows that it was actually much, much, much wetter. There's really no uncertainty there. Deserts were actually lakes and so on. It's really a very strong evidence. We propose this feedback that explains this discrepancy, and I won't repeat the feedback again. I do want to mention this again, that the feedback cannot be simulated by current climate models because they need to, for two reasons, I guess. One is they can't resolve the ocean upwelling zone because the typical resolution in a climate model is, say, 50 kilometers, while you need 2 kilometers to resolve these upwelling zones. So that's not doable. And also, they don't allow the land change to change interactively. We don't need to get into that. And also, when you have a positive feedback like that, it actually means higher uncertainty, right? Because the question is this feedback going to be triggered? What is it going to be triggered by? Is it just higher SST higher CO2 might trigger it? But when will it be triggered? We don't know. And when it is triggered, how rapidly would it be developing? So that means that there's an uncertainty. A positive feedback means a higher uncertainty in general. Great. Questions about this first part, John?
So you're assuming these separate parts, the two parts of the
Right.
separate, but the problem very difficult. So then we don't know at what level the positive feedback will equilibrate
That's right.
from that. And I guess the thing I'm wondering is, what is the factor that is damping the positive feedback that prevents it from running away to infinity and equilibrate it at a certain level?
Okay, that's a wonderful question. One would be, for example, the temperature of the upwelling water. So upwelling water comes from a depth of about 100 to 200 meters. That is the temperature difference that you see at the surface between the upwelling zone and elsewhere. So the most you can warm is this temperature difference between the depth of 200 meters and the surface. That would be one thing that would stop it. Nice. More questions? Yes?
Probably not fair, but I assume you only use the one climate model to get your results. What about the other 20 climate models available?
I don't know. That's a great question. You can't go to CIMIP and check that because they need to run such an experiment. If they do, we'll know, I guess. Yeah, nice question. More? Okay. In the spirit of being efficient. Part 2. So this is the work of Peter Sherman, who was a postdoc with Mike McElroy at Harvard, and took one of my courses, and then we collaborated and wrote a couple of papers together. Wonderful guy. And Peter Hybels, who's my statistics master. So this was a master class in statistics for me. I kept telling people for decades that I hate statistics. I'm an enthusiast now because of this work. So hating statistics was a big part of my identity, so it's gone. Okay, so what is this about? This is about the World Weather Attribution Project. That is what motivated this. So here's what that is. Again, the New York Times, my favorite source for that sort of thing. They show you these different calamities, whether it's droughts, fires, floods, and so on. And then there's a piece in the paper that says that for years, climate wouldn't be able to attribute individual weather events. They would tell you there's a difference between climate and weather, but now there's an advance in attribution science, and now we can attribute individual events. And that is what this World Weather Attribution Project is doing, and that motivated our work. And I'll explain a bit more what they're trying to do. Okay, so what are they doing? They look at, say, a record. So suppose there was a cold event in North America, 2017, 18. This is the cold event. So you see the temperatures I forget where exactly that was. I think it was never mind. You see the record over 100 years, and you see this as that specific time. And the question is it the case that global warming, anthropogenic global warming, reduced the probability of such event, and by how much? That's the question we can ask. And the answer in this case is you look at this, and I'll explain this figure a bit more later, but this is the magnitude of the event, and that is the return time. What is the typical time between two occurrences of such a cold wave? And the claim is that it used to be 20 years, but now because of global warming, we're much less likely to have such cold events, and the probability has changed to 200 years. So that's an example of an attribution. They say this event is now 10 times less likely to happen than it used to in the past. Some other cases, they would say this event is much more likely to happen, depends on the type of event. That is the general approach here. Okay, hope this makes sense. So here's a set of examples. We talked about the North American cold spill. There's the Madagascar drought, and they say, in this case, they say we can't actually decide whether this is right or wrong. I mean, they're being very fair about this. The Nigeria floods, they say climate change exacerbated heavy rainfall leading to large-scale flooding in highly vulnerable communities in Africa. So they conclude that this particular flood was due to climate change. This is the UK heat wave. They say without human-caused climate change, such a temperature would have been extremely unlikely. But now, because of climate change, it is much more likely, and they tell you by how many percent. And these evaluations are typically published a couple of weeks after the event itself. And the logic is that you want to let people know that this is related to climate change because this would increase awareness, and people would want to do something about this. Sounds like a good intention, no question whatsoever. Make sense? Okay. Okay, the whole thing is based on generalized extreme value distribution. So let me explain that for a second. So suppose you have a simple Gaussian process, like the temperature in Toronto as function of time is behaving like a Gaussian, but instead of looking at the temperature every day, which is Gaussian, I'm asking, okay, what is the maximum over here? So this is a block maximum, right? That's what it's called, block being 1 year. And you're asking, what is the maximum of this year? What is the maximum of that year? Turns out these block maxima are not Gaussian anymore. They satisfy a different distribution. That different distribution is this thing right here, which is called the generalized extreme value distribution. So it's the idea of extreme value distributions describing, for example, a block maxima. Clear? Any questions? Okay. So this is the mathematical expression, and this distribution, unlike a Gaussian, which has a mean and a variance, 2 parameters, this one has 3 parameters. One is called the location, one is scale, and one is shape. The location is kind of the equivalent of the mean for a Gaussian process. So it's convenient to think about it as the mean. Okay, so whenever I show you a mu and talk about the location parameter, you think the mean of a Gaussian distribution, and then you're okay with that. Make sense? Okay, great. Okay, to estimate these parameters, they use maximization of log likelihood. So if you're not familiar with this, it's actually not critical, but basically you're maximizing the likelihood of the observations, and using that you find the parameters of the distribution. So like the variance and the mean, except this one has 3 parameters. That's how you calculate these 3 parameters, by fitting it to the data, by maximizing the likelihood of the data points. I'm not getting into the details because this part is less important for us. Okay, now this is super important. Everything is going to be about this alpha right here. So let me try and explain what's happening. This location parameter, which we said is kind of like the mean in a Gaussian distribution, is assumed in these studies to be proportional to the global mean surface temperature. So T, it should have been T bar actually, is the global mean surface temperature. And the idea is that the mean, say, think about heat waves somewhere, say heat waves in Siberia. This will be one example soon. When the global mean surface temperature changes, you expect the mean of the distribution that describes these heat waves in Siberia to also shift with the global mean surface temperature. And the shift is assumed to be linear in the global mean surface temperature. And this alpha is the proportionality constant that tells you how the mean of the distribution, of the location parameter in the distribution, to be more exact, shifts with the global mean surface temperature. So the entire attribution will be based on alpha. So again, alpha is the dependence of the location parameter on the global mean surface temperature. That's the assumption, that there is such a dependence, and the procedure will be to calculate alpha and use alpha for the attribution. Any questions about alpha? Yes, please. I mean, if you change the mean, the variability will change as a result of that. You're asking about the other 2 parameters. They're less concerned about that. And it does make sense that you make the mean of the distribution or the location parameter change with global mean surface temperature. So I think they're doing the right thing by doing that. Yeah. Yes.
This might be entirely positive. So a Gaussian has 2 variables, 2 parameters that define it. What is the 3rd parameter here related to?
The shape, the scale, and the location.
Yeah, just like one that isn't just derived from the Gaussian itself. What is that? What is that related?
None of this is derived from the Gaussian. I guess So I guess you're thinking about this one as being the underived. This is the formula. You can see that there's a tail that looks like x minus mu divided by sigma to the 1 over xi. It's complicated. So, you know, you have one parameter is the sigma, another one is the mu, and the third one is xi. So, you know, it is what it is. You can show that if you have block maxima, this actually is the limit to which the distribution goes. So, I mean, it's a powerful statistical result. Whether 1 year is a long enough block for this to happen is a different question. But, you know, that's what they assume, not unreasonable. Okay, so we have alpha. And I think this is an attempt to explain how the attribution works. So we have a blue distribution before global warming. And I drew everything here in terms of Gaussians to just make it as simple as possible. So this is the mean of the distribution. And the mean is equal to some mu0 plus alpha t of 1900. So the blue represents the distribution in 1900 before anthropogenic climate change. And then anthropogenic climate change happened. We're now in 2020. The mean changed like this. Mu is now mu0 plus alpha of t, global mean surface temperature at this time. And of course, there's a shift in temperature. We know that temperature increased by 1.2 degrees or such. And therefore, the mean has changed. And the probability moved with it. So now we can look at what used to be an extreme event. This event right here, this high temperature, say, call this 40 degrees Celsius, was very unlikely because it's in the tail of the distribution, but now it's less in the tail and it's much more likely to happen. So once you have alpha and you know by how much the mean changed, you could also estimate how much the probability changed for that extreme event. Okay, this is 40 degrees Celsius, used to be very rare because the probability is very low here, but now that the probability changed from mu0 plus alpha this to mu0 plus alpha that, the probability is much higher. That's how the attribution is calculated. Questions? Okay. Yes, please.
Also not fair, but as you stated earlier, the alpha T relationship is assumed to be linear. So that gives the assumption that everything we get for anthropogenic temperature changes is small enough that the nonlinear terms are small compared to the linear one. For how long are we going to hold that assumption true?
Yeah. You'll see later that we run into problems even with the linear dependence. Of course, things could be nonlinear, obviously. I mean, but the question is, do you have enough data to estimate even this linear dependence? Turns out it's not so simple. So if you wanted this to have a beta plus t squared or something, there's just not enough data to estimate that's not the nonlinearity. So we can't worry about it for that reason. You know, if we had a record of 1,000 years instead of the 100 years that we have of instrumental record, maybe we could worry about that. I mean, it's a good question, obviously. Okay, so what are we trying to do? We look at 3 different cases: Siberian heat waves, Australian forest fires, and Madagascar drought. And we'll repeat their analysis and look at it carefully and see what we can suggest. The goal is to suggest tests that would tell us whether the results of the analysis are believable or not. You know, that's what we're trying to do. Okay. So the first thing we're doing, and this was an idea of Peter Hybels in this case, so we had the results, we understood what's going on, and then Peter said, let's do that. So this is what he suggested at the end and presenting it at the beginning because it's a very powerful result, okay? So what's done here is you take a very long control run. You run a climate model for 1,000 years. This is part of the CESM, Community Earth System Model, run for 1,800 years, if I remember correctly. And you apply this technique to that. Let's calculate the alpha and all of that. Let's see what happens. Now, there's no climate change here because there's no CO2 increase. This is a pre-industrial run that's like almost 2,000 years long, but we could still fit the alpha and all of that. And let's see, what do we find? We find that alpha has a value of 5. What does value of 5 mean? Value of 5 means that when the global mean surface temperature increases by 1 degree, the extreme heat waves in Australia get stronger, the mean gets stronger by 5 degrees. How could that be, right? I mean, it's possible to get a local amplification of global warming, but it seems unlikely that you'll get a factor of 5 amplification in Australia due to global mean surface temperature. Would you agree? Is it clear what we're finding? This is super important. Let me try again. So
Australia, the entire Australian continent.
it's actually, I think it's this, do we have Australians here? I should be careful. It's the southeast side of Australia where the fires were especially strong, 2019, 20, and so on. There's something Murray Basin, forget.
Yes, land temperatures more about, and if you talk about a 1 degree change, we see temperature changes on the order of 2 or 3.
That's right. But 5 seems like a lot. Would you agree? I'll give you an alternative.
It's like a small change in the medium distribution leads to a larger relative change in tails because of just the shape of the.
That's right. This is not the tail. This is the mean of the distribution of the extreme events. Yeah.
The tail of the full
Right,
distribution.
right. Fair enough. I'll give you another explanation in a second that you see will actually make more sense. Then this is the consequence of global warming. In any case, remember that there's no global warming in this case. We're still calculating an alpha of 5. So why does this happen? I think this summarizes it nicely. So think about ENSO. Suppose ENSO leads to a warming of 1 degree in the East Pacific. And suppose, just to keep things simple, that this led to a 1 degree increase in the temperatures over Australia, the mean temperature during the ENSO period over Australia. ENSO is over a relatively large area, so it also affects the global mean surface temperature, as we all know. And that effect will be small. So that leads to a 0.2 degree effect on the global mean surface temperature. So now you're trying to deduce the effects of the global mean surface temperature on Australia, and there's a factor of 5 here. So if you think, okay, what happened is the global mean surface temperature changed, and that leads to a change in Australia, then you get to an amplification of 5. But if you understand that both actually change because of El Nino, you understand that that factor of 5 is not due to global mean surface temperature, just because ENSO, El Nino, has an effect on Australia and also has an effect on the global mean surface temperature. And this arrow does not represent a real causal relationship. Did that make sense? Questions?
So the alpha is based on regression of past temperatures. That's the point. Is that right?
Yeah, you take this long record of 1800 years and you fit the generalized extreme value distribution parameters to such the location is mu0 plus alpha global mean surface temperature, and that's how you get alpha. And the reason it's 5 is that there is a local variability mode that affects both Australia and this leads to a dummy dependence here between the two that seems very large.
Some types of analysis like that, I thought one trick is to remove patterns of.
That's right. That's what they should have done, exactly.
They're
Yeah.
not doing
They have not done this in this case. Yeah. Okay, see that we have 4 minutes. Let me skip directly to something else. I think we got one idea. Another one is the following. We could just one sentence about another test. So the other test is this. When you fit a model, a statistical model to data, if you add another parameter, say you have a bunch of data and you're fitting a straight line, there's going to be a certain fit. If you fit a quadratic that has 2 parameters instead of 1, or 3 instead of 2 actually, then the fit will be better. So whenever you add another parameter, you're going to get a better fit. In this case, the other parameter is alpha. So you add an alpha and you do get a better fit. The question you could ask is, okay, I got a better fit, but is this improvement to the fit to the data real one, or is it just because I added another parameter, and any parameter I would have added would lead to that? So there's a test called the deviance statistic, or it's also called the log likelihood ratio test that you could apply. And when we apply that, this is for the observations for the Siberian heat wave. You can see that this range here is under the red line for the observations. That basically means that when you add alpha, when you analyze the Siberian heat waves, there was a huge Siberian heat waves a few years ago. So when they analyzed that, the addition of alpha was not justified statistically. Any other parameter they would have added could have led to such a statistical improvement. The statistical improvement does not cross the threshold that tells you, yes, this dependence on the global mean surface temperature actually is likely to be a result of some relevant physics. It was just not sufficient according to this deviance test. So I didn't explain what the deviance test, but it's important to me just to say there is a test called deviance statistics, and that statistic tells you that that in this case there wasn't a justification for adding alpha. Other things we've done is to ask, is it justified to use a 3-parameter distribution like this GEV, the generalized extreme value distribution? What happens if you just use a Gaussian with 2 parameters? Turns out that that gives you just as good a fit to the data. So it's not necessarily justified to use these extreme value distributions. It's actually sufficient to use the Gaussian. And if you believe in Occam's razor, then the less parameters, the better. So a Gaussian would have done just as well as far as we can tell. So, okay, and there's the last point I wanted to make, so I'm jumping ahead, is there's the analysis of the, long story as you can tell, analysis of the Madagascar drought in 2019-21. So Madagascar is one of the poorest countries in the world. That was a super serious drought event that lasted 2 years. And I think that you have these results, like it is clear that climate change likely contribute to the worsening drought. This is from the press, right? And so people talked about the effects of global warming on that and so on. This is the analysis of the World Water Attribution Project. The point I wanted to make here is that they analyzed periods of 2 years. There isn't that long a record in Madagascar, so they fit 14 data points is what they have here. So 14 data points is just not enough to draw any conclusions, especially not on extreme value distributions, which actually require, based on some other studies, hundreds and thousands of data points. So I think that's something else that one wants to be careful with. Making sure you have enough data to make the statistical, to come to the statistical conclusions that you're looking for. Okay, so jumping to the conclusions, long story as you can tell. Okay, so let's see. Here we go. So the World Weather Attribution Project is trying to attribute things to global warming. The way they do this is they make the extreme value distribution parameters, the location parameters specifically, a function of the global mean surface temperature via this mu equal mu0 plus alpha t that we talked about. They calculate the alpha there, and then they use that to calculate the change in the probability between 1900, where the t bar had one value, and 2020, where t bar had a very different value, as we know. So we looked at 3 cases. We find natural variability affects the results of the attribution analysis, because if ENSO or the NAO or the Indian Ocean Dipole or any of these modes would affect your region and also affects the global mean surface temperature, you might get biased results, because alpha is now not representing global warming as you'd like it to. It actually represents natural variability seen through the lens of global mean surface temperature. So that's one conclusion. Normal distributions or log normal seems to be doing just well enough. You may not need a more complicated distribution with more parameters. You can use these deviance statistics to tell you whether you could actually add this additional parameter alpha. Is it justified to add it? So I think that's an important question to ask. And the bottom line is that it's not simple to attribute an extreme event within a week or 2. I guess my students argue with me about this. I think it may not be a good idea to try. They tell me that I'm wrong and it is a good idea to try. Every one of us should decide ourselves. Thank you for listening. You want to do more questions?
Yeah.
Please.
Yeah, no, thank you. This is really interesting. I really appreciate this work about attribution from a statistical perspective, and it highlights some issues I haven't really thought about, and I don't think a lot of people think about. I have a question about, so the fits to a log normal distribution without GMST dependence are just as good. Well, but if what you're trying to do is to attribute to warming, then you need to have GMST or some sort of dependence on something else. So but I think just as good, you mean that like the distribution fits the data well, but it might not be just as good for, but like presuming that it's a good idea to try to do this, you kind of need to introduce that in order to attempt this problem, right?
I mean, you could do this analysis with a Gaussian. You don't have to do it with extreme value distributions. The difference is that Gaussian has less parameters, so the fit would be more robust. You have less parameters to calculate, and you don't have many data points. This is yearly data typically for that sort of analysis because it's these block maxima of precipitation, temperature, and so on. And you only have 100 data points in that case. So with so few data points, the simplest statistical model you can use, the better, and a Gaussian is simpler than GEV, and therefore it's better to use that. That's the logic here.
If I could ask a follow-up, so one workaround that I could imagine for the limited amount of data is to look at like a long simulation or a large ensemble and look for extreme events in the simulations that are like the ones that are observed. Is that like in that situation when you've got the larger amounts of data points, is it still more appropriate to just use Gaussian instead of using one of these generalized extreme value distributions? And like, is it maybe a better idea to try doing that approach?
I don't think we tried that. That's actually a good idea. We used the long integration for something else, as I explained. But it would be a good idea to see how long a data do you need to justify the transition from a Gaussian to an extreme value distribution. That's a question you can ask and answer using the available CMIP data and so on. Nice idea. Yeah.
Great,
We haven't done that.
When you say the fit or normal juice distribution with them, what do you mean? What are you fitting? I just kind of so is it?
Yeah, think about it. If you have data of temperature maxima, you could plot. You could bin the data into, so the horizontal axis would be the temperature of the magnitude of the temperature, and the vertical axis would be the probability of such an event. And you get something that looks like a Gaussian, and you're fitting a Gaussian to this probability distribution function that you calculated from the data. This is the fit.
So it's not a distribution. It's not like a distribution of the maximum.
No. So we have 100 data points of yearly maxima temperature, say in Siberia. And you plot the probability distribution function for that. And then you know about kernel estimates? Okay, never mind. So you plot the probability distribution function of that by plotting a bar plot. What is the probability of the temperature being between 20 and 21, 21 and 22 degrees, 22 and 23? And you get this bar plot and you fit a Gaussian to that. That would be the fit. All of that is for yearly maximum events, yes. So that's the idea. You evaluate the probability distribution from the data, and then you fit the distribution to that. It's done through a tool called log likelihood maximization, but that's a detail, I think. Yeah.
So if I understand correctly, you did an 1800 year industrial simulation, and then you tried to calculate all these alpha cases. Have you also tried it for when there are anthropogenic emissions to see whether the alphas change?
Yes, this was on the plots there. I didn't have time to get into this, but this was part of what's known as the large ensemble of the community Earth system model, the NCAR model. So they have both a very long control run, and they have 30-something ensemble members representing 1920 to 2020, and we analyzed both as part of the study. We can plot a distribution of alphas. Say you have 30 ensemble members, you could calculate an alpha for each. You could look at the distribution alphas. We've done all of that. But, this is sort of a detail, so I didn't get into that.
I guess my question is, so maybe alpha is not useful because of the internal variability, but maybe when you add anthropogenic climate change to it, then they become distinguishable. And you can sort of, I don't know, benchmark in various places and subtract off.
Yeah. Right. So we used that's one thing I didn't have time to talk about, but is important. We use bootstrapping to estimate the uncertainty on alpha, and ends up that, alpha needs to be positive for global warming to make, say, heat waves worse. And the uncertainty on alpha is very large. It goes all the way from negative values to positive values. So that's another thing we're emphasizing, that it's important to look at the uncertainty in alpha itself. The project does look at uncertainty in many results, but they don't, as far as we could find, look at the uncertainty in alpha. And we are emphasizing that uncertainty is super important. And we estimate it among other tools by using the ensemble members of the CSM and also bootstrapping of the observations.
Yeah, I'm interested in more detail, about using the ensemble members to, separate the anthropogenic signal from internal variability. So Paul mentioned there's, statistical methods you can use to do that. So I'm interested to know.
Oh, I know. Okay, here we go. So you see, these are the different alphas from the ensemble members. You see the many red lines are the distribution of alphas. Each distribution is obtained from one ensemble member, and it's a distribution of alphas because we're using bootstrapping on that one ensemble member. And then we do this for all ensemble members, and we get all the many distributions. So that's one of the ways we're estimating the uncertainty in alpha, by looking at the distribution of alphas in the many different ensemble members. And you can see that the range is very large. And you also have the distribution for observations in blue there. So, does that answer the question?
Like you can filter, like, have you thought about filtering methods that are meant to filter internal variability?
Yeah, I mean, the obvious thing would be to take mu is equal to mu0 plus alpha equal times global mean surface temperature plus beta times Nino3. And then the question is whether you have enough parameters for both and for enough data for both alpha and beta, but that's what you need to do. And in the equatorial Pacific, it makes sense for this beta to be times Nino3, the El Nino index. But if you're in the North Pacific or North Atlantic, you need to use PDO, NAO, and so on. So you need to use an index that represents climate variability relevant to the region of interest. So it's not as automatic as just using global mean surface temperature, unfortunately. But it's not that difficult to do. Great. Thanks for the many questions. That was fun.
Okay, so let's thank Lee again for the work.